Okay, so here's another problem that we're going to work on that asks you to draw the shear and bending moment diagrams for this frame. So like some of the similar problems that we've done previously, we're going to, first step would be to find our reactions, and then to disconnect the structure at all the connections. In this case, there's just one, B, and I'll find my internal forces at B. And then once I have all those in conditions, I should be able to draw the shear diagram and bending moment diagram for section AB and then BC. So just to get started, I'm going to assume that this thing at A, although it looks really elaborate, is really just a pin. So I'll assume that I have an X and a Y force and then over at C, it looks like it just has a bearing, no moment capacity, nothing in the horizontal direction. We'll just have CY. So our first step would be to find those reactions. Who was the last person I picked on in class? Mr. Ryan? Okay, I'm not going to do Miss Petra. She always seems to start. We'll start randomly with Mr. Stewart. You were the closest. Okay, so what do we do first, Mr. Stewart?
You want to find a moment at A?
Yeah, that's a good idea. So let's sum the moments at A. That should find, when we do that, what should we find? We should find our CY reaction. I'm going to go ahead and change this load a little bit to help me out. So what is the concentrated equivalent force for that? Mr. Sanchez, what would that be?
40.
Sorry?
40 kips.
40 kips, that's right. Now we're going to sum moments about A, so what's the distance to that force from A? Ms. Lester, what would that distance be? 5. So I think I got everything I need. And don't forget these guys here along the side. So I'm looking at all the forces, applied forces, the 10 kip, the 15 kip, and my concentrated equivalent of 40 kips. They're all creating what kind of moment about A? Positive or negative? Negative. So I'll just start with each one and work my way around. So I've got minus 10 kips times 4 feet, minus 15 kips times 8 feet, minus 40 kips times 5 feet. And then I have my reaction at CY. What kind of moment does that create, Mr. Pong? Positive. And its moment arm is 10. So what's CY equal to? Somebody calculate that already?
36.
36? Anybody else get 36? Well, we're getting a check on that. 36. Sounds good. Miss East, what would you do next?
I'm sorry.
Huh?
Some moments, the forces.
Which direction? A, X, or Y?
Y.
Sure. So let's sum forces in the Y direction. Make sure we're in equilibrium. So I assumed AY was acting up and CY was acting up. What else do we have in the Y direction? The concentrated equivalent force, 40, and it's down. So that looks like AY is going to be 4. That look right? I think so. So, Mr. Duarte, what's left? Yep, some forces in the X. So in the X direction, I have AX. I assume to the right was positive. And I've got a 10 kip and a 15 kip. So it looks like AX is negative 25. Okay, any questions about that? So the next part would be to break this thing apart about B and find the internal forces. So you can decide which free body you want to use. You want to use AB or BC. You guys choose. Let's vote. How many voting seems to be appropriate this time of year? So everybody who wants AB, raise their right hand. Oh, it's a slam dunk. AB is the winner. That's pretty exciting that you can get that many people to agree about something. Okay, so let's see. AY was 4 kips, and I got a positive value, so it's up. AX was negative, so it's to the left, 25 kips. And then I have my reactions, so my applied forces. So halfway up, I have, 10 kips. And up here at the top, I have 15 kips. Now, at B, where I pulled it apart, now I'm going to assume that BX is to the right, BY is up, and there's my moment at B. Okay? I guess the only thing I should add maybe is the distances here.
It wouldn't matter if you switched the side.
Well, you just assume whichever direction you like, but remember that when you go to draw this shear force and bending moment diagram, those directions, we're going to have to go back and use the actual shear force sign convention and the bending moment sign convention. And since we usually take the structure and we'll rotate it, this top edge we'll assume is the outside edge is the compression edge. So I've actually assumed this to be positive bending moment. Actually, this value is going to end up being positive shear, the way I've drawn it, when I look at shear forces. But that was not my intention. My intention is I just, positive X, positive Y, right-hand rule. It just happened to match up. So who did I leave off on? I started with Mr. Stewart. Oh, Mr. Sanchez, you're up. What do we do next? Did I already pass you? Oh, Duarte. Mr. Warburg, you're up.
You take the moment about B.
All right, the moment about B. There's a lot of stuff going on here. Not everything has any effect on the moment about B. The 15, BY, and BX all pass through B, no moment. What about the 4 kip force here? No. So we just had the 10 kip, the 25 kip, and then the moment. So with right-hand rules, my sign convention, this moment at B is positive or negative, Mr. Coleman? Positive. What about the moment for the 10 kip force? Positive. So that would be positive 10 kips. And what's its moment arm? 4 feet. And then the 25 kip force, Mr. Young, what would that be? Positive or negative?
Negative.
And what's... Say again?
8 feet.
8 feet. So what is the moment at B?
160.
160. That's... Yeah, 160?
Yes, 160.
Came out positive. Mr. Ryan, what would you do next? So if we sum the forces in the y direction and make sure they're in equilibrium, what do we have in the y direction? We've got BY, which is up, and 4, which is also up. So that's easy. BY is negative 4. Petrick, back to you. What do we do?
Sum the forces in the x direction.
So let's do that. Sum forces in the x direction. Lots of x forces going on here. So I've got bx to the right, positive. 15 and 10 also to the right. And then my reaction here at A, which is negative. So what's Bx? Wow, getting a lot of these. Okay. So about half the statics is normal. And now we're ready to really have enough information to draw the shear force and bending moment diagrams. So let's get a fresh sheet here, and I'll transfer that. So we'll start with, we don't have to start with AB. In fact, I don't think I'll start with AB this time. Let's just to show you that you can go any direction you like. I'm going to start with BC first. So I'm going to draw the diagram at BC. So we have a uniform load. It has a value of 4 kips per foot. The length is 10 feet. What's CY equal to? You guys remember that? I don't. Have to go back and look over here. Let's see. CY was 36, and it was up. Now we solved for by here and got a negative value. So it's actually down, which means it would be up on the other body. C has no moment, but there's a moment at B. What do we get our moment to be from before? It was counterclockwise of 160, so it's going to be clockwise of 160 here. Okay? So just transferred all my internal forces, and now I can hopefully fairly quickly and easily draw the shear force and bending moment diagrams. So positive shear, positive X, we're going to use kips. What is the shear at B? The reaction there is 4 kips up. Is that a positive shear or negative shear? That's positive. Over here on the right-hand side, we have a force acting up of 36 kips. What kind of shear is that? Positive or negative? It's negative. So I know where I'm starting and where I should end. To make sure this is all matching, don't forget our basic principles that the change in shear between any 2 points is the area under the load curve. So let's apply that here. So as I go from positive 4 to negative 36, that change in shear should be equal to the area under the load curve. Which it is. Yeah, 4 times 10 is 40, and it's down, so it's negative. 4 minus 40 is negative 36. That's good. The slope of my shear diagram is given by the load. And the load in this region is constant at 4, and it's negative. So I have a constant negative slope. So I have a little bitty positive piece and then a big negative piece. You can also see there's an area where I go from positive shear to negative shear, so that's going to be another little point of interest in my graph, and I need to find that location. I'll call it X1. So remember, the change in shear across this region, and if I start at 4 and I go to 0, that means my change in shear should be minus 4 kips. Simultaneously, the area under the load curve is what? So if I, again, project that line up and look at this area. What is that area? It looks like it's 4 times x1, right? And when you set those two together, you find that x1 is 1. That's convenient. So I have everything I need here, so it's just a matter of drawing my moment diagram. So we'll have units of kips for force and feet for length. Who did I leave off on? Who's the last victim? Oh, okay, Mr. Kimmett. She's pointing to you.
Okay.
What's the moment at B?
Positive 160.
Positive 160. And since I've got you there on the hook, what's the moment at C? 0. Well, that's some good places to know. Don't forget that the change in moment between any 2 points is the area under the shear diagram. So what's the change in moment over this first little segment of x1, which we know is 1 foot? So what's the area under this part of the curve, Mr. Preston?
1 times 4. Wait, no. Yeah.
Yeah, well, it's a triangle, so it's 1/2 base times height. So it'd be 2, and it's positive. So get out your calculators. What's 160 plus 2? Very good. Very good. I'm gonna really exaggerate that on the scale, because the next thing we're going to talk about is the slope of the moment diagram is equal to the shear. So the shear is going to start off at 4 and decrease to 0. So the slope would kind of start off at a high positive value and decrease to 0. If you kind of fit that in there, you get a little parabolic section like that. Now what's the next section tell us? Well, the change in moment should be this part of the curve. So if this is 1, that means the resulting side is 9. So the area of this triangle is what, Mr. Sanchez? Oh, was it your turn?
So 9 and it's 4.
I can't do that on the top of my head. So that's 36 times 9, right?
This is a triangle.
Hey, what do you know? It's 162, and it's negative. So that brings us to 0. And the slope of the curve is given by the shear, which starts off at 0 and increases linearly to a big negative value. So if you kind of fill that in, might get something like that. So there's the moment diagram. So what's the maximum moment in this beam? 162, and it occurs where? 1 foot from B. That's not so bad. Now, what do we have left? Section AB, right? So this is the one where I'm going to kind of rotate it over. So I'm going to draw that here. Let's start with what happened at A. So I want to know the shear force, which is AX. I believe when we saw for AX, we had a value of 25. So I should have 25 acting up. And what happened at B? We found BX to be 0. So nothing there. And then at midspan, I had a 10 kip force, and over here at the end I had a 15 kip force. No moment at A, but we found a moment at B, and we solved for that moment. Let me slip back here a second. There it is. So I assume that I got a positive value, so that means I have in this direction. Okay? Yes?
So what's more influential in the design of the beam, the moment or the shear?
Well, the beams are usually controlled by the moment. The shear just controls the connections. I mean, you do check shear capacity of your beam, but usually shear is not as important in the design of the beam, but it is in the connections. Because a lot of times your maximum shear occurs at a connected end. So if we're bolting that together, we have to choose the size and number of bolts to make sure that they don't fail in shear.
Will you go back to the other page real quick?
Sure. So see here at B, that's what you're thinking about at the moment?
Yeah, I'm looking at like where BX was.
BX is here, but BX we found was 0.
Oh, okay.
So imagine this, just rotate it clockwise 90 degrees. And you should see that. And this is 4 feet and 4 feet. I know we're just about out of time, so let me just, I'll stop pestering you guys and we'll just do it real quick. So here's my positive shear diagram. So we're going to start off with a shear of 25, and that's positive. It's a little harder to figure out what the shear will be here. It doesn't seem like there's any shear, but there's this applied load. Let's see how that affects us. And then about midpoint, I've got this 15 kip. So the change in shear is enter the load curve. No load, no change. Then as I go from the left side to the right side of this 10 kip force, I drop 10 to a value of 15. The change in shear from here to here is there into this part of the curve, again 0. And there it is, matches up. A little bit of a step. And then finally, the moment diagram, positive X, positive moment units. So what's the moment at A? 0. And what's the bending moment at B? 160. So let's see if we can make those match. So the change in moment is given by the area of the shear diagram. So what's the area of this part of the shear diagram? It's a rectangle. 25 times 4 is 100, right? So I should hit somewhere here, positive 100. The slope of my moment diagram is the shear, and the shear there is constant, so I have a constant slope. I haven't heard that in a while. And that's a 25 to 1 slope. Then the change from here to here is there in this part of the diagram, which is 15 times 4, which is positive 60, and that hits. Again, the slope is constant, and you'll notice that it's not as steep, 15 to 1. So there's my moment diagram. In this particular beam, the largest moment occurs at B. Okay, any questions about this? All right, thanks for being patient. Welcome back from spring break. Oh, there is a question.
How come you say shear on the first one is negative 36 and it's going up?
On the right-hand side, force up creates negative shear. On the left-hand side, force up creates positive shear. Remember, if it tries to make the object move clockwise, that's positive. So if you push up with 36, the element will want to go up counterclockwise. That's negative.
Dr. Camp, did you say you have our papers?